Good morning. We are going to see the topic link budget and link margin. Okay, link budget. Before that, we have to see impedance matching. Maximum power is transferred to the load when load resistance is equal to source resistance. This is the criteria. When load resistance is equal to source resistance, maximum power is transferred to the load. If the load is a complex load, then conjugate of the power source of power is needed. If the load is complex, then the power transferred is maximum when the source is conjugated match up to the load. Conjugated match to the load. High resistance leads to high voltage and low current. Low resistance leads to high current and low voltage. I'll come again. High resistance leads to high voltage but low current across the load, and low resistance lead to high current and low voltage across the load. Now, link budget. Link budget in a communication system, the link budget is the difference between minimum expected power received and the receiver's sensitivity. Link margin is also written as LKM. Link margin, minimum expected power received minus receiver's sensitivity. How much minimum amount of power is received by a receiver and receiver sensitivity. Receiver sensitivity is nothing but below this level, the receiver will stop working. That is called as receiver sensitivity. Receiver sensitivity is defined as a receiver power below which the receiver will stop working. So this has to be fixed in a communication device for good signals to be reached. So it is generally in dB. Example LKM. If the minimum expected power received is 40 and the receiver sensitivity is 10, then the LKMS value will be around 40. This value should be um, the lowest. Below this value, the system won't work. This is link margin. Okay. When we design a communication system, we have to fix at least a few dB of link margin to allow attenuation. So this minimizes the loss. So as I told you before, for a good communication, link margin should be designed. This link margin below this value, the system won't this will communicate properly. So link margin has to be fixed. Then link margin and link budget. This is the diagram for link margin and link budget. Here, the transmitter sends signal via cable to the antenna. The antenna will transmit in free space and it will reach the signal will reach the receiver antenna. Then again, the receiver antenna is connected to a cable that is in turn connected to a receiver. Okay. Here, initially the power is being transmitted. That is shown in green. This is distance versus power dB. Okay. Here, when the transmitted power is given, when it goes through the cable, there will be a loss of signal. This loss may be a contact loss or due to heat loss or ohmic loss within the cable. So there will be a small amount of power which is lost within the wire within the wire. Then again, the antenna will increase its power by using EIRP. That is EIRP is one minute. Effective isotropic radiation power. The antenna will use a concept of effective isotropic radiation power. With that, it will increase the received power, and then the signal is again being transmitted in the wireless. This is wireless communication, so it is through air. So when it travels through air, the signal is again being and the power will get reduced. This may be due to the atmospheric changes, rain, or due to fog, or due to high-rise buildings like that. So the power of the signal will be reduced. At the receiver antenna, the receiver antenna will increase the received signal by using certain techniques. Again, when it is that is shown in green. Again, when the signal is sent to a cable, then due to the losses, the small amount of current will be lost, or power will be lost, and that will be given to the receiver antenna. So receive power, and this is power margin, a link margin. So the margin below the sensitivity. This is receiver's sensitivity. So below this, the transmitter, the receiver won't work. So the link margin is being fixed. So with the help of link margin, we can design a better system to reduce attenuation. Attenuation is nothing but loss, power loss. So working, the transmitter transmits power, as I told you before. The transmitter transmits power. Transmit power is connected to the transmitter via a cable, and it is connected to the transmitter via a cable. Okay. When the transmitting power from the transmitter is sent to the receiver, when the transmitting power is sent from a transmitter to the receiver, there via wireless communication, there will be loss in the transmission due to free space. So due to free space, there will be a loss. This loss is shown here. There'll be a loss. At the receiver end, the signal is received by receiver antenna, and the data are transmitted via a cable. It is received by an antenna, and the data are sent via a cable. Cable to the receiver device. Okay, from the graph. From the graph, the graph is power versus dB. Power is dB versus distance. This is the graph. In the graph, the transmitted power, there's certain range. While traveling through the transmission line, there will be losses due to heat and contact. The transmission line, there will be a loss due to heat and contact. So this is represented in the red line. So this is shown in red line. Mm, in red line. After the transmitting antenna, at the transmitting antenna, power is increased using EIRP technique, effective isotropic radiation power. So maximum power of the transmission. So with this, maximum power is transmitted from the transmitter. So the value of the transmitted power so this is the value of transmitted power in the transmitting antenna. In the next phase, it is in the next phase it is radiated in free space, which is affected due to path loss. This reduces the power transmitted to a certain level. This will reduce the power transmitted to a certain level. At the receiver side, and certain improving techniques is used to improve the signal, as I told you here. Certain techniques are used to improve the signal power there. Then at the reception end, it receives the power is got loss again. So this is what I told you all this before now. That is what is written here. Okay, at the reception side, the actual power, the power is got. For the system, we already estimate a sensitivity value. For example, say 10 dB. If the receiver power is below 10 dB, then the receiver won't work. So the link margin of the system of the receiver point plus minimum receiver sensitivity. So link margin of the system is received power minus receiver sensitivity. So that value is link margin. So in general, link margin is prefixed before any application based on the application. So based on how much power we want to receive, the link margin is being fixed. The next one is being fixed. All this is I've already told you. The system is with this uses by associating link margin, the system works properly as per the requirement. Without any extra cost, you can design the system easily. So this is the advantage of using link margin. The next one, link budget. Link budget, it is an accounting of all the gain and loss in the transmission system. So at the receiver power, how much transmitted power plus gain and loss. Transmitted power plus gain minus loss. This is the link budget. Here we ensure that the loss must be within the link budget. So we'll already fix a link budget. So the losses should be within this link budget. Okay. So link budget for equation is this PR, that is receiver power is equal to transmitted power gain of the transmitting antenna minus loss of the transmitting antenna minus Fs. free space losses. When it is transmitting, it is free space losses minus LM. LM is losses fading due to polarization effect. Okay, and plus receiver gain minus loss in the receiver. So all this is the equation for linked state budget. Thank you.